So welcome everyone to today's session from the Julia User Group Munich, this time about concurrent programming. We are going to look into asynchronous and parallel programming. And for today, I have a little notebook prepared for you. And it was actually, again, a little bit extra difficult to compile it so that you can use it, but I made it. So I just now sent the link in the chat so that you see it. And yeah, so this is the notebook, and I myself am going to use it now. So you just have to pass this link into your browser, and there we get very with big thanks to the Leibniz Institute in Germany. They give the resources, the compute resources. It will soon spawn such a notebook environment for you. So I'm using the very same. So this is quite beefy. We have 8 gigabytes of memory and can actually experiment a little bit. I'm Stephan Sahm, organizer of this meetup in general. And yeah, so I'm always doing these one-on-one sessions kind of every second month, and every other month there is going to be a speaker, invited speaker. And this year, yeah, I started then directly with the 101 part again. So today we're going to look through 3 aspects, and I hope to be ready by 8. So the 1.5 hours in total should be enough. Starting with asynchronous programming, because it's also the easiest to do on on this environment, which is somehow big, but still kind of not so big. Then we'll look into multi-threading and parallel computing at the end. So mind that this is really kind of a simple environment. So unfortunately, we are not going to look into big data, but yeah, we'll at least see kind of the methods. We can call everything, so we can really have the feeling what Julia looks like when used in this concurrent programming setup. And then, yeah, you can use the same code kind of somewhere else where you have a bit more memory, a bit more processes. So on your laptop, for instance, and yeah, and then try out the big data part. Okay, so let's start with asynchronous programming. As said, so I have a look on the chat, and yeah, so just give me a clue there or raise your voice if you have questions. This is a Jupyter notebook. I'm always using Shift and Enter to run a cell and move on to the next one. But you also have this run button here at the top. And yeah, let me actually, yeah, full screen is probably even better for today. So this date is just for some helpers. It's just the time package of Julia. And the first thing I want to define is a little countdown function where we come about this async macro. Macro is a special kind of function which can rewrite the code. And yeah, this function starts usually from 10, and then from 10 going with -1 steps to 0, we count down. And of course, we want to count down by seconds. So this is a lovely little example of how asynchronous programming can work. And if we just run this, we see that the process directly returns. So we are again here and can execute whatever we want. And yeah, meanwhile, all the time, the countdown still continues. And yeah, thanks to the iJulia kernel, the Jupyter kernel, we still see the output. So despite we are now in a new cell, the output of the asynchronous process is still print out. So that's actually a feature. If you go to Visual Studio Code, Jupyter, this won't work, unfortunately, but thankfully in the Jupyter notebook. So being here, we have the full insight to the concurrency. So you see, we can just execute anything and it will continue. But how it works, yeah, we are now going to look a little bit more into the details, how it works. And yeah, to understand it a bit better, we define an alternative sleep function. And this sleep is going to block in the sense of continuously calculating stuff and doing things all the time. And this is kind of an expensive sleep if you want. And yeah, so if we look at kind of the sleep blocking versus the sleep, we first execute a countdown and then our sleep, and then we check that we are awake again. We see that if we do the blocking, nothing happens for 3 seconds, and then the countdown starts. So this is kind of the key thing to asynchronous programming. It's still only one thread on a single process which is doing the job, and it's managing itself like which part, which so-called task is currently running. And yeah, so if you see it like here, then if our thread is occupied by doing something else, by doing the sleep blocking, nothing can go on in the countdown. It really waits all the 3 seconds. But if we use the standard sleep function, we see that the countdown actually starts already, and our awake comes after 3 seconds, and the countdown continues. So this is kind of the key thing in Julia. If you use something like sleep, you give space to the Julia scheduler so that it can switch the task and use the current thread to do something else. Okay, so let's get a bit interactive. So you hopefully have this notebook in front of you, and yeah, just some little task. So my first little exercise here is to print the current time in addition to the countdown, because it may also be because of the printing, which is delayed. So it might actually not be due to the asynchronous processes, but rather because the printing is blocked. And with the timestamp, we see directly where things are, when things are created. So yeah, that's my first little exercise. So you can write here, but this exercise is actually a bit easier if you just go up to the definition of our countdown function. And yeah, and now somehow insert also the current time. So there are multiple options actually to do this. I'm I'm speaking slowly intentionally so that some of you can solve this without me showing the solution. And yeah, and we've seen already one function in the meantime. I just skimmed over it, but you may have noticed it. So we actually see the function which gives us the current time in a kind of nicely formatted way, actually. And we can use the same syntax here. So this is a string, and with this dollar sign, we are interpolating values. So for the one new to Julia, this is definitely a super crash course, but I hope you're going to enjoy it nevertheless. So with this dollar sign and put in parentheses, we can also insert dates now and have another countdown. And yeah, so with this, we can kind of check, in addition to the countdown, also the time when it was created. There was a little hands up. That's also one of the ways to communicate in Teams. Thanks. If there's a question, please just ask. If not, all fine. I continue. So now we see the timings here, and we can also see, still thank you for introducing the feature. And we can kind of also see it here that they just continue afterwards, and then in a 1 second difference. And here they just continue 0, 1, 2, 3, 4, and it's all as expected. Okay, so next question to get the idea is, what would happen if we use the sleep blocking and the countdown in the first asynchronous task? So just to remember, so we used sleep blocking here in our main interactive part, and if we go to our countdown, you see that we sleep here. And we could also use sleep blocking over here. And before executing it, I mean, it's only a function, we can execute it here, it doesn't do anything. Yeah, it's kind of interesting to understand what is going on now. So what would we expect here? And what would we expect here? And yeah, just yeah, you may have made up your mind. So it's actually very similar here. And here comes the difference. So if the countdown itself is blocking and does not use the normal sleep, it does not give back to the scheduler, so that our main process has no chance to run. So this sleep just never is going to trigger, and hence the awake will just be at the very end instead of here after the third countdown. And yeah, and this one is just the other way around because it was asynchronous, and it's, I guess, a little bit random which part gets the first hit. But yeah, probably because we are still in the process and we are still running, the sleep blocking is the first which gets the hit, and afterwards the scheduler gives the control to the countdown. So this is what is happening.
Stephan, could you just
Yeah.
very quickly show the syntax again for the change in the code?
Yeah, you're welcome. Thank you very much for the question. So this is our countdown function, and before it was this like the standard sleep function. And now we used kind of our alternative sleep function, which is all the time doing stuff. And yeah, and in this sense, blocking the current process. And this is a crucial difference. So yeah, is asynchronous programming. It really is key to use the standard sleep, as this is non-blocking and gives control back to the Julia scheduler, which then can put other tasks and let them run.
Thank you.
Thank you for the question. Yeah, so yeah, you see kind of in general, it's very simple to do Julia asynchronous programming. You just use this async macro in front of your code, and you can, with the begin and end, put as much code as you want. And yeah, it's really just standard code, and this will then be executed as a task. Is sleep blocking a custom function? Thank you for the question. Yes, it is. It is. So I zoomed a bit into just to make it easier for the recording, but it's actually defined just below. And because of the countdown, we have a lot of filled up space. So let's have a last look at sleep blocking. So what does it do? It first checks what's the current time, and then it computes kind of where we want to go. And this we just do a simple plus, and using the dates second, we're adding a couple of seconds to our current time. And then we just continuously do a while loop. And this while loop, so yeah, thank you for the question. I haven't went in the details here. So this while loop is really just doing constant computation. It will always check the current time and check whether it's still lower than the date where the time where we want to come. And yeah, so this is the simple idea. Okay, yeah, thank you very much for all the questions. It's very important, especially at the beginning, to get everyone on board and have a common understanding. Okay, so the first message here is that I hope that you now can understand why the sleep function may actually sleep much longer than you specified. So if you sleep for 1 second, this also means that you give the control back to the scheduler, and some other task, which potentially lasts for an hour, may get the chance to control the process, and your sleep of 1 second may actually last for 1 hour. So that's kind of important to keep in mind, but this is part of the idea of this asynchronous programming. So yeah, if you use a lot of asynchronous programming and you want to prevent this, it's helpful to have a couple of sleeps in between to really ensure that Julia can sidestep to another task. Okay, so that was the most important function, the async and the sleep. And now let's take a look at some further, wait and fetch. So if we have our countdown, yeah, we can also define it just like this. This is the task, and we can wait on this task. So this was a bit late actually. and wait means that we block until the task is done. So we see now that here we have this nice star, which means that this cell is still computing. This because wait now really makes the code blocking. So while the task was running in the background, wait on the task is now blocking also the main interactive task here until it's done. And there's another version of it. This is fetch. And with fetch, we get the return value of our task. And yeah, so this is the very same. You can speed this a bit up, counting from 4. And the result is nothing, which is Julia's default return value. So here comes the third little exercise of today. So yeah, what do we need to change to get another return value of our countdown task? So yeah, this is again a dummy placeholder. You can experiment here further, but it's again easier to go back to our countdown task and take a look. So this is the function, and functions have the return value at the end. So this block here is actually the return value of the function, which we have seen this. This is the task. So if we call countdown, we get the task. And the task itself can also return. And this is actually the last statement of what is within this async block. So here's just a for loop. And actually, this doesn't return anything. By default, it returns nothing. But we can return something here. And yeah, by just having it at the last line. And this should be it, actually. So give it a try, return something different, whatever you want. And I need to go to my countdown and fetch. So fetch is, as you see, blocking the very same as wait does, and it gets the return value. And here you see that we actually really get the string all done. Okay, so that's for the beginning. So then let's speed up a little bit. But yeah, if you have questions, please always ask. So there are a couple of more calls, and sync call is another macro, which is quite helpful here and there. It synchronizes multiple async calls. And to show this, I'm just building up another function, countdown blocking, which will actually call wait. So yeah, that it's not going to be in the background only, but yeah, we are actually waiting for it, and print something before and print something after. And now we can see what sync does. So I am executing a sync here on 3 async calls, and they are all just starting. And because we use the standard sleep, they are all running in parallel. And yeah, and finally, I'm printing all done. So you see that the sync is kind of an implicit wait that all the things in here, and it's really kind of by it's so-called lexically enclosed. So all things which you write out here will be waited on, and the all done is really the last thing after all countdowns ended. So this is really nice and makes also visually a nice code. And yeah, you may want this. Okay, so notifying condition. Now I'm kind of going through a couple of more details just that you know. And this is about how you can speak from one task to another, and especially about triggering these tasks. And for triggering, there's the condition object, which is there actually just built in. It's exported by default. You can just access it. And we see if we wait on this condition object, then as of now, nothing happens. And we need to call a notify method. And then our task actually gets running. So it was waiting on this condition to be triggered. And then we triggered on this time. And the condition now works this way, that if we do this again, the task is again waiting, and we need to, so take a look at this seconds, it's 49. And if we need to notify it again, so here's 12. And then we see that the task will run again. So this is a condition. Yeah, mind my comment, think of it as a trigger. And there's another way, standard way, how to trigger such asynchronous tasks. This is called an event. And I would suggest to think of it as a state, actually. So it looks a bit more complicated. And you also need to access it with qualified, in the qualified way, base.event. And yeah, now we do the very same. And we see, okay, the task is again waiting to be triggered. And if we notify the event, it gets triggered again. So what's the difference? It's so completely identical. The key thing is now that if we rerun our asynchronous task, it will directly work. So the event is set to an on state. And as long as it is on, it will, yeah, every task waiting on it will succeed immediately. And yeah, the way to reset our event to off is with the standard reset function. And yeah, and now re-executing this async block will actually not print directly, but just return the task. And we need to notify the event again to set it to an on state. Okay, so this was triggering with a condition and an event. Yeah, can be very helpful depending on what you want to do. So this is about giving you the basics. And the next one is really key. Okay, there's a question. Thank you very much. So say I have condition 1 and condition 2. Can I wait on the first of the two conditions that triggers? Well, it's a lovely question. So yeah, so yeah, it's an easy way just doing it. So there's, I don't know of a built-in function which does this directly, but you can kind of simulate it easily. So if you have an async, yeah, which, and you wait on condition 1, then you can notify a common condition, yeah. And you have an async waiting for condition 2, then you can notify a common condition. And then you have another task, which is your main task. You wait on the common condition and do whatever you want. And this should solve exactly your problem. Thank you for the example problem. And definitely you can write nice high-level code to make this in a single function call. But yeah, it's great to see that it's that simple. Okay, so the next thing I want to show you is the channel construct. And this is kind of the key means of communicating, actually not only in asynchronous programming, but in all kinds of concurrent programming. So this is really important to see. And yeah, and unfortunately, I see a little mistake of mine. So this should be without the for. If you're following this, please also delete the for to begin with. And yeah, so we are constructing here a countdown channel, again, counting down from 10, because I'm usually counting down from 10. And the syntax now looks like this, again, a new syntax. And we are using do syntax, which constructs an anonymous function. So this thing is really just taking one argument, we name it channel, and then doing this. And we put this anonymous function into the channel. So here then finally, there comes an anonymous function as this first here only argument. Okay. So this is how we can construct it. And we now calling sleep first, and then the function which is key here is called put. And we put our element onto the channel. So we can create this channel, and now we see that this is not a task, but really a channel object. And yeah, the raw way how to communicate with it would be something like this. While our channel is still open, we take an element from the channel, and then we're going to print it. So as you see, this is really just like the normal countdown. And yeah, the reason why it's like normal countdown is actually a bit more specific. But let's first see another syntax. So we can also just use a standard for loop, which will do the very same, but not now. Okay, so what happened? It doesn't do anything. And the reason is we just used all the elements of our channel. We need to recreate our channel so that it still has elements in it. And then we can use also the for syntax and get all the elements printed out nicely. So this is very, very intuitive that you can use for loops to access channels. Okay, so thing is, I deleted the for because the channel without an argument will pass only a single message at a time. So yeah, it's if you put something, then the channel will this put operation will block if there's already one element. So it will sleep in the sense and wait until the channel is again empty, and then it will put the next. And with a channel of 4, there's a buffer in the channel. So if you call put and there's one element, it will put the next. And then there are 2 elements in the channel, and then again there are 3 and 4 elements in the channel. And the 5th element, this will again wait. So the 5th element will again block, and wait until the channel has another empty slot. Yeah, so this is another little task. So change this to another value, maybe 4, maybe something else. And yeah, it would be perfect if you can give it a thought what would change. And yeah, so you see that the countdown was now really counting down second by second. And this is kind of the key thing. I'm going to give it again the 4. So if you give it with the 4, then you've seen that it was already 10, 9, 8, and then it was the 7. So what happened is that this asynchronous process was already doing its stuff. And actually, I was a bit faster. Yeah, so it had a buffer of 4, but we have only seen 3 parts already filled in because it still takes its time. It's still sleeping until it puts the next element. But if we wait kind of a bit longer, 1, 2, 3, 4, 5, we see that all first 4 elements have already been collected, and then it continues. And depending on whatever value you set here, you will see kind of, and how quickly you execute the next line, you will see that these elements are indeed buffered. So yeah, nice little application of our countdown to see that this actually works as a buffered communication way. Okay, so there's another little thing I want to show you, and this is kind of and the next little exercise. So if we exchange sleep and put, we have actually some extra difficulties. So what I mean is if we do this the other way around, which may be more intuitive, then actually let's now simplify things. I want to have it standard counting down session setting. So if we do the for loop, everything will actually work out nicely. Just that you've seen this, the for loop is in the sense a little bit more complex. So if we do this while is open, then things will actually, unfortunately, break. So yeah, So it's the channel is closed. It tells us, despite we have this check, it's open. And yeah, and just to see to explain to you what's happening. Yeah, so we put things, and we take um, our element, which we just put in, and then almost immediately we are going to print, and then check whether it's open. And this is so fast that's actually still within this sleep period. So yeah, our task is actually indeed still open. We just don't know that won't give any further elements. And yeah, so our is open will be true despite there's nothing further to take. And yeah, the take will now block until the task is actually done, and will then realize, the channel is closed. Nothing to get, and throws this exception. So that's just a nice little difficulty. So yeah, keep this in mind. But good news, the best syntax anyway already deals with this nicely.
I'm sorry, I'm a little confused. The channel's open, you just block because no new element was put during the sleep, right? But the channel's still open. So
Yes.
why where did the channel get closed?
So the channel, so the bit more details. So the channel is kind of the data structure for communicating, and what is in
Yeah.
here is really just an asynchronous task which communicates with the channel, and they are bind in such a way that as soon as the asynchronous task is done completely, the channel will be marked as closed
Okay.
and not before. So this little is open check is in the sense not enough. We would need to wait for the next element or no element to really be sure that we are not in this in-between state, that the task is still doing something, in this part sleeping, but yeah, not returning anything new to the channel.
Okay.
Thank you for the question. Another question about the do syntax. So yes, so another simple way to rephrase the do syntax. Wait, just let me. Can I? Yeah, I have multi-line editing mode. I love this. And yeah, so this is equivalent. And then doing all the rest. So let's clarify the do syntax a bit more. Now I'm running the countdown. Okay. So yeah, nice little difficulty. Okay, so then I jump to multi-threading. Thank you all for the questions. And multi-threading is actually, from the summary, super easy. And hence I put it at the top. So you simply, instead of async, use spawn. And almost everything else works out of the box. So you can use wait, you can use fetch, you can use all these event handlings, and you can even use this add sync macro to summarize code that you want to wait on all the asynchronous processes in the code. This works all for threads as well. Yeah, you just need to replace the async with threads.add spawn. However, threads are really dangerous. So yeah, it's actually it's good mental exercise to understand what's the difference. So a thread is something is kind of a line of machine commands which are run by your operating system, and the operating system is going to say, oh no, this thread runs, and now this thread runs. And this is not so much under control of Julia, because on the operating system level. And hence you can have a task switch at a really difficult place. Yeah, and the async is in this sense much better to control, much easier controllable, because here you really only have the task switch at a dedicated place in your code, namely at the sleep or at the put or at the take or at the wait. So you have specific commands where you know, okay, here it's usually safe to switch the task. And yeah, with the threads, this guarantee is not given, but you can really switch at any place in your code, which is usually yeah, giving extra problems. So here the official warning from the drill documentation, actually somewhere in the whole thread, but I found this to be most condensed. So they write, multi-threaded programming has many inherent difficulties, and if a program using threads exhibits unusual or undesirable behavior, for instance, it crashes or mysterious results, thread interactions should typically be suspected first. So if you never worked with threads, take this serious. This is really often the case because it's so easy to crash your stuff and have weird interactions going on. And yeah, so there's really some truth behind this that you should suspect thread interactions as the first cause, as the main cause for some weird behavior. So that would be now my little question to you in the beginning. So yeah, don't know. Let's have a little 3 minutes exchange, if you like. So do you have some further thoughts, some further summaries why you think multi-threading is more dangerous than asynchronous programming? I would be really interested to hear just other thoughts on this. If not, it's also fine. So if some of you have already worked with multi-threading, yeah, it's really it would be helpful, I think, for others also to hear another phrasing of what the danger is actually about in multi-threading. Okay, I take the question for later. Okay, feel welcome to just share your thoughts sometime later. I'm then just continuing with a couple of stuff about threads. So threads have kind of a couple of helper functions. For example, the number of threads and the current thread ID. So the main process is always the main thread has thread ID 1. And the number of threads is actually fixed if you start at Julia. So you need to add a special environment variable or a special command line. It's actually Julia minus threads equals 4, for instance. But in this case, actually, I had no control over the Julia command because it's all wrapped in this my bind interface. So I needed to set some Julia environment variable. I just you easily find it in the documentation. But yeah, if you have access to the Julia command, this is the easiest way to say I want to have 4 threads. And yeah, and then we can build another threads countdown, which really just more or less does the very same, but using a spawn. And as you see it already here, I'm doing a little bit extra. I'm using core printer now, and I'm using the sleep blocking. And yeah, it will just add to the warnings already told. But let's see how it works. So we now have a threads countdown, which is like a, in the sense, well-defined function which you can put to a thread. And yeah, and we're now executing it. So just that you know, I'm already outputting also the current time to have a better understanding what's going on. So I'm first outputting the current time now when I start the cell. Then I'm starting the thread countdown. Then I'm having a blocking sleep of 3 seconds. And then I have another awake also with the final time. So if we run this, everything is blocking. Yeah, all the sleeps are blocking. So with asynchronous programming, there would be no concurrency yet, whatever, because yeah, it's all blocking. So there's no task switch happening. But with threads, we see that despite we used sleep blocking all the way, we see here a nice increase of seconds. So The countdown started 5, 6, 7, 8, 9, 10, and somewhere in between at 8, there was the sleep blocking, which finished, and we have this awake. So this is the idea of threads, that they are even concurrent despite you have blocking code. And yeah, so this is handled by your operating system. Okay, now to the some other question already, please. Okay, if not, then there's a question in the chat for later, just reading it. What would you recommend for writing a data frame simultaneously? Ran into some troubles when writing results into one data frame when using threads. Okay, so this question is actually really good for even later. I have to think about it. I have no immediate recommendation. Mhm.
So is each of the other threads blocking with the sleep blocking? Is the sleep blocking being applied to each of the threads separately?
So in this little example, there's only one other thread. So this is the counting thread, the countdown thread, and the main thread where we are still continuing executing stuff. So and there's no asynchronous call which may kind of give a hello scheduler, hello Julia scheduler, please switch the task. But it's really just continuous code. It will compute. And the same here. It will just compute. And nevertheless, we see that the tasks switches like we want. So it's real kind of parallelism. So not sure whether I understood your question or whether this kind of clarified things.
The main thread blocks or sleeps for 3 seconds, but the countdown thread continues. That's the point, right?
Yes, that's the point. So if you would try the same with the asynchronous above, we've seen this, then the awake will definitely be at the bottom or at the top, depending on which one gets first. Yeah.
But you're not executing the countdown on multiple threads. You're only executing the countdown on a single extra thread.
Right. So we have this spawn macro. So this add is always called a macro in Julia. And all this code is executed now on one other thread. And actually, please.
And I'm assuming later you're going to show us how you could spawn the code to execute on multiple threads at the same time.
Actually, I'm not going upon this, but yeah. So in principally, so what you can do is really very simple. Yeah. So this would already spawn multiple threads, and just to have this a bit more self-explaining. So I had here a little print in the beginning, and it's actually printing the thread ID.
Okay.
So yeah, this way it's right. So if we now do this, we have actually 3 threads going in parallel, and they are running on different threads. So the first on thread 2, then thread 3, and thread 4. So it's automatic. Yeah, it checks which thread is idle, and will spawn the process, the task on there. And because we continue doing stuff here, it knows that the first thread is not idle but occupied. But actually, the last one, to the best of my understanding, was a bit random. So it could also have scheduled the last one on the main thread, because also on thread 1. So there's no reason why it wouldn't spawn on thread 1. This is one of the difficulties, actually. Yeah, you see, it was really random. So we had success. Now it was scheduled on this main thread where we interact on. So this is also good to know. This can happen if it's idle, and then it will just take it. And as of the current Julia version, there's almost no way, and with default built-in stuff, to prevent this. You need to use another package for that. we'll mention this in a second. But this now you see this is now really kind of 3 threads which count down all in parallel.
Thank you.
Thank you for a question. Yeah, so as already told, we have many things work out of the box, which is really nice. However, there are a couple of things also to consider. And yeah, and this apparently simple example is not so simple. So there are a couple of issues, not only with this example, but this was also actually put. So if we use, instead of the core.println, we choose standard println, things will already break. And same is if we use not this blocking sleep, but an asynchronous sleep. Also, this will break this independence. And this is really surprising and actually a bug. But yeah, this just shows quite well that things are really difficult. So this would be the way you would write it kind of, yeah, intuitively, because why not use the standard sleep? So if you have another asynchronous process on this thread, so this is at least my intuition, it would run. But this is not how threads work. This asynchronous scheduling, yeah, this is somehow intertwined with the threads. And if we, I just delete this one here. You've seen this. If we now do our interaction again, so you see it should be, the awake should be in the middle, yeah, somewhere in the middle. So this is not what's going on now. So we have the awake now at the beginning. And yeah, and I think if we change the first println, then it's going to the end. Oh no, it's going after the first. So yeah, it's weird interaction. Yeah, so this just should be one of the warnings. So threads are in the sense well tested for the case where you compute stuff. Yeah, you need the other thread to speed up your code, to do things in parallel, to compute things in parallel. It's really another use case as for the asynchronous task. The asynchronous one is rather I'm waiting for some event and don't know when this happens, and if it happens, I'm only doing small stuff. Yeah, but I want to be able to wait in an efficient manner. And the threads, on the other hand, they really are built for doing heavy computation. They are expected to run all the time. So yeah, so this println is already, is that you get an intuition why both the println and the sleep are kind of difficult is because the println itself communicates with this asynchronous programming. So yeah, println uses also some primitives similar to the sleep. At least is my best understanding of it. If you want to understand more, you're welcome to go to this issue. But so far, I think there's not so much on top of it. But yeah, some help how you can circumvent this in case you want. But yeah, just one of the issues. There are other issues with threads and still other ones. So I've linked here 3 issues. So be warned that threads are not that easy to deal with. And this even in addition of having kind of data race conditions and making sure that you really can work with the operating system switching your tasks so that tasks can be interrupted in between. Okay, so still things will improve over the next Julia versions. So I guess that all these parts somewhere will be solved because this is also one of the big goals for Julia, that you really have proper and best thread support, also in combination with the asynchronous and the parallel computing, which we say later on. As of now, still there are many really good use cases for threads, and and the one package which I want to recommend you is thread pools. This also solves the issue with the main thread, so that you can ensure that other threads are only spawned somewhere else and your main thread still stays interactive. So that may be one use case. And a similar, and then there are some extra tools kind of really for scheduling multiple jobs on the threads. And one similar similar function is already built in. We see this in a second, the threads macro, which is also mentioned in the question. Then there's a threads X package, good to know, which speeds up many built-in functions, any sum, what's this, product, anything else which are going over some vectors and has kind of some associative meaning, so that it's not depending on the order. So this is also for the transducers package. This is about stream transformations, and also here, if you have an aggregation over in stream, this is also perfect for threaded parallelization. And if you use one of these kind of already packaged supports for threads, then of course you can also be safe that these implementations they all respect the difficulties of threading. So they worked out the details, they did their homework, that this is actually safe. Okay, so finally on this thread part, one last warning. So we now see the threads macro, but what we also see is what atomic operations mean and what it means that the operating system can switch your threads just wherever it wants. So what do we do here? We just for 1,000 times, we are adding +1 to our accumulator. So this is a so-called reference. And just to show this, so if we do this, if we just do the brackets, it's accessing the element in there. And if we combine this, we add +1 to it. And if we're accessing it now, it's just, yeah, updated to 1. So this is used quite a lot in Julia code because, you have usually immutable structures, and the ref is kind of a mutable structure, which you can put wherever you want. So we are adding +1 1,000 times. And if we do this with the threads, then our computation is parallelized to all the threads that we have available, which is 4. And yeah, and you see that now the sum of 1,000 ones is 750, which is a bit surprising. But this happens because threads are running in parallel, and it happens that a thread switch happens kind of in between, that some thread is reading the current value, then updating it, and then writing it again. And then some other thread was also reading it and writing it, but this overlaps, unfortunately, so that the other thread's update was just destroyed. And yeah, and the way to circumvent this is to use something what is called atomic operations. And here, for example, there's an atomic add operation. So yeah, there are more things to atomic, but now this atomic add guarantees that nothing can go in between. So either this +1 is respected, or it's blocking until there's time to actually do this +1. So now the threads are waiting in order to really do their additions. So this is important to keep in mind. And yeah, so I hope there were a lot of warnings. So please, yeah, if you use threads, be cautious and read documentations proper. You need to read about logs, and yeah, read also about the atomic operations. So yeah, that you get an understanding what you all need to do. There's a question in the chat. Thank you. Yeah, this thread atomic functionality is indeed coming from a newer Julia version. I don't know whether it's 1.7 or 1.8, but I fear it's not yet available in the standard 1.6 latest long-term release. Yeah, so 1.7. Yeah, the long-term release, long-term support 1.6 is not yet equipped with atomics. Very good point. Thank you for making that point. still very useful, and which also shows that the Julia team is heavily working on supporting threads. So yeah, this atomic operations is a big addition and really a very important addition to write safer code which works with threads.
Can I ask a question? Sorry,
Yes.
I don't want to. The whole point of the thread of threads is parallelism. So, using the atomic operation, have you basically eliminated all the parallelism in your code? I mean, it would be interesting to do the timing on both of these.
Yes, definitely. It's going to be slower. So let's have some time using. There's a nice macro b time, and it should print the timing. So benchmark timing is doing a couple of extra runs to also prevent the pre-compilation overhead. We see that here we have microseconds. So the atomic add is doing a kind of okay, wait, this is just the opposite around, isn't it? Okay, so the atomic add is apparently very much optimized. Wow, I wasn't aware. So it's much quicker. I have no clue why. It's definitely specific Julia code behind it, so it's especially supported. I was imagining it to work with logs, standard logs, like I put the links here, but yeah, apparently it's not.
Can you maybe increase the loop size? I'm not sure if it if it's just optimized because it puts everything on one and because it's so small.
You are so right. Yeah, let's make this. Yeah, okay. Thank you for adding this. So this is a pity of presenting and thinking. Okay, that still might not be it. Let me check. This one was giving the same results. And we just used. So this is just one execution. Okay, threads does not return anything. Okay, so I'm very sorry, but this seems to be especially hard. So it does not give me a shared representation. And so I would need kind of a, I would need a kind of task object, but the sync does not work on threads. So actually, this was one of my open questions. I haven't tried this. Sync is supported on almost everything else, but apparently not on this thread macro, which is a pity, and hence we have a hard time testing this. But still, so I think the threads is then blocking. So if it doesn't return a task object, it's blocking, and in this sense, the B time from the beginning was totally adequate. So let's just give it one last try. So I'm now timing the whole thing, and I'm doing the same here. And yeah.
Okay, so now it's behaving the way I would have expected.
Yes.
Right, with the atomic taking longer.
So good question why this was different the first time. So why putting B time in front of the threads generate is somehow, doing weird things. Yeah, so now we have the expected timings. And I also guess it's the most trustworthy way of testing it so far. So yeah.
But notice you got the right answer this time, right?
Yeah.
Yeah, and
So
the
it takes
allocations
more
didn't
time.
explode because B time, I think, ran within the thread because the
Say that
allocation
again.
exploded before.
I couldn't hear the question. Could you say it again?
No, yeah, the allocations exploded before. Now you have the same amount of allocations approximately, and before it, I think it was in the thousands.
Yeah.
Yeah, that's why it was not comparable.
Thank you for noting that. Yeah. Just.
But why is the output correct now, whereas before it was incorrect?
So the note just now was that we have now comparable allocations, so that what is executed is more or less the same. And if we just do the B time on the threads itself, then we see that we have a factor, 1,000 more allocations, and 24, 26, but this is a 2,000. So it definitely does something completely different. So this is,
Yeah, no, I see that.
not trustworthy.
But I
So
went back to the earlier point of the accumulator result was incorrect before, and now it's correct.
The B time is run multiple times in order to sample, and so the accumulator was never reset to 0, and or when we were running it just on the threads.
Ah, okay. I think so. I may have not understood the comment just now, but yeah, for me it also looks like the B time is forcing everything to be on one thread, and hence we don't get a speed up due to parallelism. So this would be my, oh, okay, now we have 200, 500. Okay. Not sure what's going on, but at least we see that it's at one time returned to wrong answer. Have I lost you? I can't hear any.
No, I'm just, I don't understand why we got an
Yeah.
incorrect answer, then a correct answer, then an incorrect answer. That makes no sense to me.
Yeah. So my best guess is that the benchmark time is somehow reducing the number of threads. So yeah, that if it's 1,000, one reason why it could be 1,000 is that there's only one thread, and hence nothing can be overwritten. That's at least one way. But I would also expect kind of some more random numbers. So 500 still looks kind of surprising. Yeah, and so it's definitely doing some other threading. If we just execute the threading code, we get much more random results. At least is my best guess. Yeah.
Are there any utilities to tell you how many threads actually got spawned?
Maybe we can print it. We can, no, I think now not so much. Yeah, so if we use time, this is the standard Julia built-in instead of the benchmark time, we would really preserve the randomness of the output result. With yeah, something with benchmark time. Yeah. Okay, thank you also for the comment. Yeah, it's really yeah, I'm not sure actually. So benchmark time should also work with lower or super fast functions by executing it multiple times. But yeah, might also be reason. Yeah, so at least we see kind of that the time prevents this randomness, and we also see not so good actually. Yeah, but we see some overhead in the single execution number. So yeah, this would be a good request to a discourse page. What is kind of a good way of timing threaded code? If the B time does not do it, whether there's an alternative. Not sure, because it would really be nice to have a little helper which accumulates a couple of runs of this, so that you don't have to do it yourself. Now it's kind of the other way around, but I guess yeah, on average, the plain threads macro without the atomic is faster. Okay, thank you all for this little investigation. So now maybe it's time to go back to this the specific question, just to have another thought on it. What would you recommend for writing a data frame simultaneously? Run into some troubles in writing results into one data frame when using threads at threads. Yeah, so just a little note. So the data frame is a big array. Or yeah, each column of a data frame, so of a table, is probably represented as an array. And the standard documentation for threads always warns for writing arrays in these threads. You need to be cautious there. And what is recommended is to I'm confused. I confused myself. No, actually, I would guess that it's actually safe. Yeah, the threads access the very same object, the very same data frame. So it should be in some way pre-allocated. Yeah, if the arrays could be pre-allocated for the data frame, that it's already of the size you want, and you're just filling in the arrays, then I think it should work. Not sure whether this is possible with the data frame API. Don't know. Yeah, and extending the data frame in different threads is probably one source of difficulty, because then you really need to make sure you're switching at the right moment. So you need locks, and then yeah, it probably is not of any use or not of much use. Yeah, so I think yeah, it could be pre-allocating data frame or writing to the data frame authors, so the authors of the package, and ask them whether they have a good idea, because this is quite specific also to the data structure you have at hand. So yeah, giving the one or the other representation of the data frame different styles of parallelized writing would work. Okay, so finally you see that my notebook got the state of being killed by my binder. This probably also happens to you, but it was actually taking a long time. So usually, and I'm going to change this soon, usually you just have to go to the top and click the launch binder button. But the standard binder interface is just too weak for our case, and it was not building this notebook, unfortunately. That's because we are already at the 12th iteration, and we summarized a couple of packages so far. But doing the link which I shared in the beginning, I just share it again here. Executing this link again will work, and I'm going to change it soon, that all these buttons will also refer to the alternative binder system. So now I'm back in another notebook. Nothing is executed, which is fine, I think. And we've been at the multi-threading part. So what's yeah, thank you also for the comment in the chat to solve the data frame task. Okay, so this was we have only a couple of minutes left. This was my part about threads. Yeah, so now let's take a look over the distributed parts. I fear I need to skim now over the last parts. So distributed means now doing things on really completely different Julia processes. So these can be on the same machine, but they can also be on completely different machines. So the memory of these processes is completely separate. And hence we don't get this interaction which we had in threads. Hence, yeah, distributed programming, parallel computing is a bit safer than using threads. But also you need to manage kind of the communication between these processes. So we start, usually every Julia process starts with one process, and here we can actually add further processes from within Julia. And because I'm not sure how many extra processes this environment will take, I just had one extra process. And oh, I executed it twice. Now let's see. Okay, now we have 2 extra workers. So this is also the difference from distributed to threads. Distributed has a distinction between this main process, which we are already running in, and extra processes created by add process. And these are then collected into or named workers. So we don't see the 1 here, but we see the 3. And oops, up. I think it's process ID. No, this is distributed. Data. Okay. No. Okay, there's also a way to access the ID, but I just don't know it yet right now. So which ID you are running on. If someone knows it, please write in the chat. Okay, so distributed, because you're now running in completely different machines, possibly, they are actually not initialized. And to execute stuff on completely different machines, there's a special macro here from distributed, which is called everywhere. And yeah, and here now I'm executing everywhere that I want to load the interactive utils package, which gives me access to the var info function, which shows the things which I defined in my current process. Because I just re-executed, there's almost nothing here, but I re-executed the countdown function. So we at least see something here. Now, if we want to run something on another process, we use the spawn add macro. And with the little any in front, we can then say it's arbitrary on which worker you distribute this. But yeah, some worker, so one of the 2 now, and it returns now not a task but a future, but it works very similar. So again, we can call wait and fetch and all the like on it. So this works very neatly, and we see that on our other process, there's actually there's not this count on variable. And yeah, if we now look at the var info here, we also see the future which we just defined. And this is also, of course, not there in the other process. So this is just to illustrate that these other processes are really empty in a sense. Yeah, they have main and core and base and distributed especially, but other than that, they are quite empty. A little detail, yeah, the spawn at any is actually calling the function next proc, the next process, to check where it's going to spawn the next process. And you see it's very stupid. We'll just take the next free process. Okay, so yeah, we can kind of do what we do with this spawn at. You see it's really just another macro. Sorry for moving too much. The spawn at is actually just wrapping a function called remote call. And here there are some benchmarks, some performance issues, why there are also special functions, remote call fetch. And this is also, there's also another macro, fetch and fetch from, which will combine the scheduling, the spawn, and the fetch into one call. And this is much quicker then. So this is just kind of the alternative way to spawn something on another process. Okay, so just Yeah, okay. Ephesus, yeah, okay. I guess we're a little bit over time, but bear with me. I just do a bit longer today, maybe 15 minutes. I hope that's fine. Yeah, the recording will be uploaded to YouTube. If you need to already drop out, that's of course totally fine. You can check the last minutes then on YouTube. Yeah, I just go through the last part still. I'm very thankful for the lively discussion today, and yeah, I find it very valuable. So I think that's good to take the extra time then. Okay, so what I want to show you is that the distributed package has a little bit of magic when it comes to bringing data or variables to the other processes, because this is the key difference to what we've seen before. The asynchronous programming and the distributed programming, it's running in the same Julia process and sharing all the variables. But here now, everything is kind of empty in the other processes, and we need to bring data from one to another. And let's say we have kind of one mattress here. So you can imagine this can be quite big, yeah. And if we use our spawn add, and for here we can, instead of any, also put the process ID, and we spawn it in process 2 and fetch it. And then we can take a look. It's now I'm using another macro. So the fetch from, I get some extra noise here. Okay, sorry for muting, but that was a little bit disturbing. Okay, so you see now we are fetching the we check what variables are defined on our second process, and now there's another A. So we summed our array on the second process, and by doing this, I'm also implicitly transferring this A. So yeah, this is just a special feature, and this is not only transferring it. This would also be kind of be with the local variable, which you won't see in the global namespace, which we are accessing here. But because this is kind of a global variable, which we're accessing, it's also defined as a global variable on the other process. So you can easily imagine now that things can get out of sync. And also, yeah, that you need to clean up your process somewhere. So this is important to know. If you use the remote call fetch, you can actually have extra arguments after the standard call. So we pass a function here, and now this argument we can pass as another argument or a remote call. So I hope you get the idea. And with this, we are circumventing this global definition by just putting it into a local function. And if we take a look now again, so this remote call fetch has the process ID here as a second argument. So we are also really running it on the same process, and we see nothing. Yeah, so the B was not defined. And yeah, important to know, this remote call now in the fetch version has actually also some magic like the spawn macro, and this is sense super magic. So yeah, I actually wasn't expecting that this works at all, but it does. And it's now analyzing the function code which we send and checking, this B is actually a reference to a global variable, and hence it does the same as in the beginning. Now we have the B also defined there. So yeah, this can be surprising, and yeah, but it can also be very helpful that this implicit data handling is done for you. So if you just want to try out some stuff, yeah, then it might not be so important, or yeah, it's great to have the data there. This is done implicitly for you. Just one way, if you want to use this magic, yeah, so no extra arguments, but everything is taken from the surrounding, but you don't want to define these global variables, there's a Julia syntax called let. So we see a lot of different Julia syntax today. So the let is another one. And this introduces a local scope and allows you to redefine outer variables. So by having this weird C equals C, we're now defining a local variable C, which has the same content as the global variable C. And with this, now actually the yeah, the implicit handling sees, okay, this is only locally defined. It's still, as you see, it works, yeah. It's still transferring the data that needs to be done, but it does not define this global reference. And if you someone see, oh, I defined too many global references, they take too much space and I want to delete them, or someone, there's also a clear function. And yeah, you need to pass a symbol, which is, yeah, with this double colon and then A. And then you see that it's not deleted, but practically it's deleted. It's set to the value nothing and occupies 0 bytes on the system. So yeah, this was the little part about the distributed. And I think it's only a small part left, but still kind of one little task for you. I think this is the last one. Just that you can see also the benchmarking here. Remote call fetch looks really weird, really a bit extra, but yeah, it makes sense. And yeah, one way to test it is again to use the benchmark B time or the timing. And yeah, if we have only one process involved, so I don't fear any interference. So so please go ahead and try some remote call fetch and some fetch remote call. So yeah, remember the remote call takes a function as the first argument. And this is how we define for example, yeah, an anonymous function which takes no arguments. It's an empty tuple. And we can compute whatever. And yeah, and doing some random number stuff is kind of a good idea. And then we need to set as a second argument the process ID where it runs. And yeah, and this little example, we want to compare the fetch. So let's check whether this works, this runs. And yeah, so it would be, for example, one check. And I need to import benchmark tools. I was remembering I did this already, but I changed the notebook in between, so it's not loaded. And yeah, we see kind of some numbers. And yeah, actually, that's good to know. Yeah, if you press if you enter semicolon at the end of a command, this tells Julia that it does not output the final value. So we only see the timing. Okay, this is the one time, and then let's add the other time. So this is just remote call and calling the fetch around it. And it's really the very same syntax. So we can just leave the arguments as is. And this, yeah, if everything works out, it takes longer. Okay, yeah, it took longer. So, and it takes impressively almost, yeah, twice as much time. So I have no clue. We can look into the code, but I think it's better for another time. Yeah, I have no clue what's the key thing which you can optimize here, but apparently you can optimize something. And yeah, so if you heavily relying on this, it makes sense to use the special function. Okay, so what I also want to show you is one example. It's a bit more complex. You may also go through it in detail on your own. But if you want to have a more complex communication between workers, this is again possible using channels. There's a special construct called remote channel, which then has a function, anonymous function like we saw just now, but it constructs a channel object. And here again, this is the size of the buffer, and this is the types it can hold for a little bit more optimized coding. And yeah, we have a couple of jobs in this scenario, and we have a couple of results. And yeah, every single job is reading something from the jobs it has to process. It takes one value from the jobs, has a random execution time. Now we call the real standard sleep. This works now without any problems. We just sleep for some time, simulating that we do stuff. And then finally, we put what we done to the results. And this is now a combination of our job ID, which was just our message, the execution time, and it's called my ID, which is really the ID of the job. So let's check this. My ID should be 1. It is. Nice. Okay. And so we make a couple of jobs by just putting numbers onto this channel from 1 to n. And we have now 12 such messages which should be processed. And we call this asynchronously. And there's a little function here, error monitor, which does something with the standard error output. I just copied this from the standard documentation. And so this is putting the jobs into place. No sleep here, it's just all putting to the channel. The channel is now filled with the jobs information. And what it's now doing is that for the number of extra workers which we have, in my case it's now 2, and lucky everything works so far, it calls not remote call, but another, we call it remote do. It's very similar, but just doesn't return a future. It just does whatever it's put, and and will do its stuff. So you can't wait on a remote do. To see that something like this also exists. And you have to specify the process as the second argument, as always. So this is the worker, it has the process number, and then you give the arguments to the function. So this is the standard remote call syntax. And that it was expecting, let me move a bit to the top, jobs and results. And exactly those we are handing over as the additional arguments. And now we check also some timing. There's another macro called elapsed, which times this code. And this is a bit cryptic, but I just took it from the documentation so that you will recognize it again. There's just a for loop counting down from N12 to N1 and checking all the results and outputting them. So if we now do this, we see that the workers are running, and so they do all the jobs. Actually, they do it almost in the right order, but we even see here kind of a switch and which task finished first. And we see also that they've been working on different processes on the 2 and the 3, but never on the 1. So this is also kind of key difference, and we see how long they simulated doing something. And so this is I really like this example of more complex communication between these different processes. They can now work on completely different machines and still work fine. So the channel is the key thing, and here you just need to wrap it into a remote channel object, but it's the same idea of communication, take and put, and things that will block and things will communicate with one another in the intuitive manner. Okay, so last bits, there's also some convenience helpers, a distributed macro, which will compute a couple of things. So here 20,000 times a random coin flip, and we'll add everything. So this is a special syntax here. Before the for loop, there can be an operator which then sums up everything. And there's also pmap, just that you've seen this, if you don't know, which you can kind of, just like a for loop, do things for every element and spread the computations to different processes. So map is a common term. It's more or less synonym as a for loop. And here we compute the singular values of a matrix. So this is then a simple function to distribute your code. If you want to go more in here, there's shared arrays, which gives you a large array which can be accessed from multiple processes, but they need to run on the same machine. There's also distributed arrays, which distribute a large area over multiple machines and chunks. And there's also a data frame if you want to distribute a data frame, but more generic, a D table, distributed table, where you can do the same with a table construct. And the very last thing I want to show, and this is it then, that there's Actually also something like an async or thread spawn available for distributed programming. So you've seen that there was a lot of complexity here in the distributed package. It's of a lot of use. Yeah, it's used in many packages and really great that it's there. But for just a user getting started to distributed programming, ignore this warning. It can be kind of just a bit much to start with. Still, it's good to have seen this. And it's still also good to see that there's already an alternative, and this is Dagger. So I'm very happy we also had the author of Dagger already as one speaker. And yeah, and Dagger is actually really built around this spawn macro, which will just work, or which tries to work intuitively as you guess. And you see that we just execute code, it's spawned. Now it's not a task, it's also not a future, it's a so-called eager thunk. Anyway, it works, and we spawn some computation on top of it. And yeah, and this is now building up an acyclic graph in the background, knowing where things are executed and spawning it at the right places, taking care of the communication between the processes. And yeah, and you just have kind of to wrap your code into the spawn, and then it's automatically distributed on the machines. And it can also be safely run within other functions. So this is a really lovely helper. And yeah, probably I should have told you this in the beginning, but yeah, this is my ending. So thanks to the work on Dagger.jl, we also have a very easygoing way to distribute code on multiple machines. Yeah, flexible and individual way. Okay, so summary, I just skim over it. We have asynchronous tasks. We went over them. So doing stuff on the same process, more or less waiting for events. That's one of the applications with multi-threading, parallelizing stuff on the same Julia process. It's difficult. Be careful with this. We have distributed computing, which then really separates stuff on multiple machines. We've seen this, and there are other packages also, MPI and Elemental, for example, which have other approaches to distributed computing. Worth checking out, but yeah, different approach. And just to note, there's also GPU computing, and it's really awesome in Julia, but it's one of the things which are just not showable within my binder because there's no GPU in the back. But it's the best GPU support in any language, I guess, which is there. So it's also worth checking out and part of parallel computing. Okay, so thank you very much also for staying the extra minutes with me. Yeah, I'm glad you joined today, and I'm there for further questions. Thank you very much.